it's great weather to listen up to things about combustible dust. So I'm Brian Edwards. I'm with CTI. CTI, we're an environmental and safety consulting firm with over 30 years experience in North America. I'm director of engineering there. As far as combustible dust goes, I sit on NFPA 61, which is the standard for food and agricultural dust. I also participated, went as a guest to 664 about wood products and 652, which is the overarching standard for combustible dust. So in general, combustible dust is a major hazard in the solids handling industry. And so today we're going to talk about the basics of combustible dust. What are the, what makes it such a hazardous material? Where are those hazards located, and when do those hazards arise? We'll go into NFPA standards a little, and then finally we'll talk about how do you conduct a dust hazard analysis. So what do we mean when we talk about combustible dust? So NFPA says that combustible dust is a particulate solid that presents a fire hazard when suspended in air, regardless of size or shape. So in layman's term, if it can burn and hangs in the air, so if you can grab a clump of material, throw it in the air, it'll sort of waft around, it'll form a cloud, and that's something that can burn, then that's a combustible dust. Typically, these would be dry foods, plastics, wood, rubber, textiles, basically in most organic materials, but then also some non-organic materials like metals, if it's fine enough powder. Basically anything that can oxidize, so if you get like aluminum oxide, so if you have aluminum powder, it can oxidize and it can burn. So with combustible dust, it's important to know that a decrease in particle size increases the rate of combustion. So my example here, think about if you have an entire log, a whole tree, if you set that on fire, it would burn for hours and hours. But if you chop that up into smaller pieces, it burns a lot faster. And finally, if you get sawdust, you get something like sawdust that can burn very fast. And especially if you mix it with air. And the reason for that is it just goes back to the fire triangle. So if you remember, and I'll show a slide later, but you have three components of the fire triangle. You have fuel, you have oxygen, and you have ignition source or heat. So that oxygen is a critical component of why things burn slower when they're larger. Because that fuel in the log, most of that fuel is inside the log. It's not touching oxygen. So you have to burn from the outside in. So you have to burn away the outer layers before the inner layers are touching oxygen. But if you have sawdust and you disperse that in a dust cloud, all of the fuel is ready to burn right now. And it will burn right now. It'll be a flash fire, and it will it will go. So what are we talking about when we normally talk about combustible dust? What size are we talking about? Historically, we talk about something that's 420 microns. So that's normally a US number 40C. But really, what you just want to consider, if a particle can be suspended into the air, it doesn't matter if it's 420 microns or not. That particle isn't conscious. It doesn't know, oh, I'm greater than 420 microns, I'm not combustible dust. There's actually been tests of like sawdust and salt materials. You can have over a millimeter average particle size and it still acts like combustible dust. But this is what it typically looks like. So if you have something like coarse table salt or granulated sugar, that's normally about the size that we're talking about of particles that you're worried about as far as combustible dust. But again, the easiest way is if just grab the material, throw it in the air, and then you'll know maybe it's combustible dust. So as we talk about the hazards of combustible dust, there are a few definitions I just want to get out because I'm going to talk about fires, I'll talk about deflagrations, talk about explosions. I just want to make sure we're all on the same page. So fire, it's the rapid oxidation of a material. And it's a chemical process. So that's one thing to remember is that fire, we think about fire, oh, it's something that we cook food with or we warm ourselves with. But really fire in and of itself is just a chemical reaction. So what happens is you have oxygen mixing with something that can oxidize, and it starts as a runaway reaction and it goes so fast that it just produces a lot of heat. A deflagration is where you have a flame front that propagates through a combustion zone. So, and basically the part of a material or part of the dust cloud ignites, and that fire that starts on one side produces the heat that burns the rest of the material. But you just think about it, it's just a flash fire, so it moves through material. So a deflagration is different than something else you might know of as a detonation. So the difference is a detonation, that pressure, the flame from the pressure wave moves faster than the speed of sound. So a deflagration is going to be less than that. So it's not like gunpowder, it's not like munitions, but it still is a rapid flash fire. So an explosion in our context is basically going to be the increase of volume of an enclosure, and then the catastrophic failure that releases a lot of pent-up energy, will release shrapnel, things like that. So when we talk about explosion, again, we're not talking about an explosion like a bomb. That's something that's going to have that supersonic blast wave going out. But what we're talking about is a vessel or structure or building that has an increase in pressure inside because of the deflagration, and then the vessel itself ruptures and causes the explosion. So again, I mentioned the fire triangle. So you have those three components: the oxygen, the heat, and the fuel. And when we get to deflagrations, you just add one component to the fire triangle. So sometimes you'll hear about it called the deflagration square. So basically, you have the three things you need for a fire. You have the fuel, you have oxygen, and you have the energy, the heat source. Then the fourth component you need is you need that fuel suspended in the air. So oftentimes, people say, oh, well, I'll take a blowtorch to my material and it doesn't burn, or it just smolders, it doesn't do anything if they put it on a pile. And the reason is some materials, if you normally try to burn it, it might not burn that easy. Because it really needs a lot of oxygen. So if it's just sitting there on a pile, on the floor of your factory, or on a ledge somewhere, it might not burn that easily. But if you get it suspended in the dust cloud, you get that, that fourth component, that suspension in the air, then you can have a deflagration of something that maybe normally doesn't burn too easy. But if you get it really mixed up with oxygen, get a really rich environment where it's just ready, then it can burn. Typically, having all four of those conditions in an industrial plant, it's sort of rare. So if you were to walk into a room and it was at a thick enough concentration that you had a dust deflagration, you wouldn't want to be in the room. I mean, you probably would not be able to see across the room. So most of the time, it really happens due to upset conditions, or there might be inside pieces of equipment. So you probably have processing equipment if you're handling particulates, or if you're causing attrition of larger materials that maybe dust comes off, some dust comes off, and the larger particles go somewhere else. You might have a dust cloud inside the pieces of equipment. That's where you'll most commonly see the potential for a deflagration would be inside a dust collector, inside a silo, something like that. That's where you'll have that. And it's called the minimum explosible concentration, so the MEC. If you do industrial hygiene, you think about the PELs. The PELs might be in the milligrams per cubic meter, something like that. The MEC for most combustible dust are going to be in the orders of a gram per cubic meter. So it's a lot. It's 1,000 times more than what your typical IH standards are going to be. So if you go in there into a building and it's maybe fuel oil dust and whatnot, it doesn't mean it's it's an immediately dangerous situation. If you reach the MEC, you would definitely know it. And the main reason is it has to be a sufficient concentration. So unlike industrial hygiene, if you get just a particle here, a particle there, and you're breathing into your lungs, those individual particles can hurt you. But with combustible dust, those particles have to be close enough together to where when one catches fire and has just a little bit of flame, it's close enough to the next particle that it ignites it. And then it's close enough to the next particle to ignite it. So it has to be a thick enough cloud to where that flame propagates through, because the size of the flame for one individual speck of dust isn't that big. So you have to have a lot of specks of dust to get that flash fire. So one way to think about it is if with coal dust, if the coal dust was at concentration, at the minimum explosible concentration, you wouldn't be able to see a 25-watt light bulb 2 meters away. So about 6 feet away, it would be that thick that you wouldn't be able to see that far away. So hopefully most people don't work in environments like that. So when deflagrations occur, they release energy in the form of heat very rapidly. So a fire generates a lot of heat. So that heat does two things. One, it heats up the air, and like a hot air balloon, when you heat up the air, it expands. But then also that solid material, that dust, when you burn it, it turns into gas. So gas is about 8 times the volume of the solid material. So if you have a little speck of sawdust, you burn it, the gas is going to take up 8 times more space. So you get just a rapid increase of air temperature in that area, and just the space that material takes up increases very rapidly, and it expands. And you'll get a pressure wave that'll go through. So as that air and as those gases are expanding in an area, it creates a pressure wave. So that pressure wave is going to come in front of the fire. And that's where you'll get that pressure wave will come through, and it'll actually lift up dust that's sitting on surfaces. So if you don't have a good housekeeping program and you get a localized flash fire, that pressure wave is going to move forward, basically shovel up the dust that's on the ground. Then that dust that gets shoveled up, it's going to catch fire. And that's when you'll have these catastrophic events where the fire will just rip through a building. And eventually that pressure wave is going to expand to encompass the whole building or the vessel where it occurs. And then the building or the vessel might not be able to contain that pressure. That's when you'll have dust explosions. So basically the dust explosion hazard, so if you're wanting to look at your facility and say, where are the hazards? This is what you want to consider. If you have the potential for there to be a dust cloud and to have ignition, and there's oxygen, and if you enclose that, so if it's enclosed with a building, a room, or some type of container, then you have the potential for an explosion because that pressure that's generated from the deflagration doesn't have anywhere to go. So it starts building on the walls of the vessel, it starts building on the walls of the building, and eventually the strength of that vessel or the strength of the building won't be able to hold that pressure in. So you can get very large pressure build up during a deflagration. And then when that structure ruptures, that's when you have an explosion. And it's a catastrophic release of that pressure that's built up inside the vessel. So most dust explosions originate inside pieces of equipment, as I mentioned before. So you'll often have it start inside equipment or a container. In industrial operation, the places that are most common are going to be dust collectors. So dust collectors account for 50% of combustible dust incidents. Most of those are fires, because with the dust collector, you're pulling the fuel into a filter. And so, except for when it's doing a filter pulse, the fuel is not suspended in the air actually in a dust collector. You think it is, but most of the time, that fuel is stuck on the filter. But every 15 seconds, every 30 seconds, something like that, you get a filter pulse, it knocks the fuel off, then you'll have a dust cloud. So maybe for 5 seconds before it sucks up against the filter. So 80% of the incidents inside a dust collector are actually fires, because 80% of the time the fuel is stuck on the filter. It's only when it pulses that it is in a dust cloud. So you're not going to have an explosion unless you get that filter pulse, you get the dust cloud in there, and that's when that ember hits the filter. But places where you almost always have a dust cloud are going to be silos and bins during filling. Just because you have the large particles are going to fall down, they're going to deposit in the silo, form basically sort of a cone inside the silo. But then the smaller particles, the dust, as you're filling, they're going to be suspended in the air. They're going to be floating around in that void space in the top of the silo. So you almost always have a dust cloud, depending on the material you're handling, if it has different particle sizes. you're almost always going to have a dust cloud in the top of a silo or bin during loading. At that point, you just try to reduce the ignition sources. So if you don't have that fuel, or you don't have the energy going into the silo, then you can have a dust cloud, but you don't have that potential for deflagration, you don't have that explosion, as long as you don't have that ignition source. Also, you'll have dryers and ovens, because if you get dust in a dryer or dust in an oven, you do have that ignition source in those pieces of equipment. So you want to pay attention in those units and downstream of those units, because that's when you start generating ignition sources. And then also conveyors and bucket elevators, things like that. Whenever there is a connection, or you drop from one conveyor to the other, you get a chance for those big particles to separate from the fine particles. You could have dust clouds in those transitions. That's why a lot of times, if you do have dust collection on conveyor systems, they'll be at those transition points. They'll be at the drop inlets. They'll be on the cross connections, things like that. A lot of people might have seen this before. It's an explosion pentagon. It's just an easy way to remember those 5 conditions. So if you have the fuel, you have oxygen, you have the dispersion of the dust cloud, so the fuel has been mixed up. If you contain that dust cloud in a vessel, then the only thing that's left is the ignition source. So if you have those 5 components, then you have the potential for a dust explosion. And NFPA recognizes this. They've recently added that, how important it is to have that credible ignition source. Because there's, tens of thousands of silos across the country, and, you're not having 10 explosions a day. I mean, there's always a dust cloud when you're loading a silo. And it's that ignition source, really, that it's a final component to make that explosion possible. Here's another visualization. So if you just have that dust cloud at that dense enough concentration that we showed earlier, and you contain it in a vessel, and then you provide an ignition source, that's when you could potentially have that dust explosion. So I have some illustration of basically a process equipment explosion. So here we have a dust collector, and let's pretend that filter has just pulsed. So that filter is just pulsed to knock the dust off of the filters. You have an ember that comes in through the inflow line. It's going to hit that dust cloud, and it starts an ignition. Those little particles, that they ignite the next particles. Before long, you have a growing fireball. As that fireball grows, you have the pressure will build up inside the vessel, and it's going to build up to a point to where it's really stretching the limits of what that dust collector can contain. And eventually, it's going to rupture and it's going to explode if you don't have any way to safely release that pressure. So one common way to protect a vessel like this, and in today's presentation, I could spend half a day talking about dust explosions, so I don't go into too much of, how you do protection, but one way you do it is you have weak points of the vessel. So you control how that pressure is relieved. So if you see dust collectors with blowout panels or rupture panels, what it's doing is that pressure, when it's building, instead of rupturing the whole vessel, it's safely released out of something that you have, maybe a pre-scored section that it pops open like a Jiffy Pop container or something like that, or maybe it has a chain panel that will blow out, and that way it relieves that pressure in a safe manner instead of the catastrophic failure of the vessel. Another way, since I'll just briefly go into it, another way is explosion suppression. So they have systems that would have a detector that as soon as that pressure wave is going into the vessel, they would have a cannon that basically within 5 to 20 milliseconds, it detects the pressure wave in 5 milliseconds, and it will release and extinguish within 20 milliseconds. But it basically will flood the vessel with sodium bicarbonate, which actually stops that chemical reaction. So it stops the flame, stops the fire before it builds up so much pressure that it ruptures. But again, I could go into explosion protection techniques for hours. We don't really have that much time today. So in an industrial setting, dust explosions can create a chain reaction, resulting in more explosions and flash fires. So flame fronts can travel through ductwork from pieces of equipment to other pieces of equipment. And then inside the building, those pressure waves that happen from the initial explosion can disturb the settled dust in the air, creating a dust cloud that permeates throughout the whole building. When you've had past explosions or catastrophic accidents at facilities, you often, the narrative is that you hear sort of like going off like fireworks. So you hear a pop, pop, pop. And that's as that flame front goes through connected pieces of equipment, it starts, blowing up other places. So it'll travel through ductwork, it'll hit another vessel, another dust cloud, that will explode. And when it gets outside of the equipment, and if you create a dust cloud in the room, that's when you can have an extremely bad secondary explosion, which we'll talk about in a second. But here I'll show you how it travels through the ductwork. So this setup, you have a cyclone. That would be your primary collector. So if you're transferring solid materials, you'll often go to a cyclone. That way the large particles that you're trying to get from one point to another will fall out. And then that nuisance dust that is still trapped in the air, oftentimes it'll go to a secondary collector, dust collector, to get the finer particles. So let's say in that scenario that we had before where you have the baghouse explode, that flame front can travel against the flow of air. So the air is flowing from the cyclone to the baghouse. But that flame front can travel faster than your conveying air. And it's going to go back, and then it can cause that other explosion in connected pieces of equipment. So a lot of times what we'll have here is you have isolation in the ductwork. So you might have some type of sensor. If you have a blast panel in the baghouse, it'll have some detector that knows, oh wait, there was an explosion in the baghouse. You'll have a fast-acting valve or some type of, if it's an active system, that will shut off that connection in that ductwork. Or you might have a backblast damper, which is a passive system that basically has a flapper. So that, as I said before, the pressure wave goes in front of the flame. So you'll have that pressure wave will come before the flame. It'll slam a valve shut. And then when the flame comes, it hits the valve and it doesn't go back to other pieces of equipment. But by far, the greatest hazard of combustible dust are from secondary explosions. This is an image that OSHA had in their National Emphasis Program to illustrate what that is. So you have a primary explosion that occurs in a vessel inside a building. And if you have dust accumulation on surfaces, even overhead surfaces, so you might do a great job of housekeeping on the floor or levels where you can reach, but unbeknownst to you, the rafters or the purlings 20 feet up are just covered in dust. Well, if you have a primary explosion that sort of creates a shock in the facility or creates that pressure wave going through, it can knock the dust off the surfaces, it can lift it off the ground. If you have control rooms, it will clean off those control rooms that haven't been cleaned off in 5 years. And that dust that just got swept off the surfaces, it becomes a larger dust cloud in your building. And then that oftentimes a flame or some other ignition source can cause a secondary explosion. And this is where you have really catastrophic accidents. So this event is what got OSHA started when they reissued the National Emphasis Program 11 years ago. Imperial Sugar and near Savannah, Georgia, and Fort Wentworth. 14 people were killed, 36 were injured. It was such a massive event that it took the U.S. Chemical Safety Board and OSHA 19 months to investigate it. They ultimately determined that inadequate design, so they enclosed a conveyor that didn't provide any way of extracting the dust from that, so it allowed there to be a dust cloud inside the conveyor. And it was poorly maintained, where bearings weren't maintained, and it created an ignition source. And then the reason it was so decimated is because poor housekeeping. There was just snowdrifts apparently of sugar in that facility, and when this happened inside the piece of equipment, when it got outside and started hitting those accumulated piles of sugar, this is what happened. A more recent incident, this happened a couple of years ago at Gideon in Cambria, Wisconsin. So this happened at a flour mill or corn mill. So there are 19 employees on site. 5 of them were killed and the other 14 were injured. So 100% of the people on site were severely impacted by this event. Luckily, that occurred during the night shift where they had basically a skeleton crew. If that occurred during the day, it would have been worse than Imperial Sugar, most likely. So OSHA stated that, initially a failure to correct the leakage and accumulation of highly combustible grain dust was the reason why this was such a bad event. The Chemical Safety Board is still investigating this, so we're waiting to have the final report.
When did that happen?
This happened in 2017. All right, so we'll talk a little bit about NFPA standards and how you can use those to help ensure the safety of your facility. So there are several standards that exist to prevent dust fires and explosions. Currently there are several standards. Ultimately, it might go to a single standard, which I'll mention soon. But basically, the National Fire Protection Association, it has staff, but it's also a volunteer organization. So members like myself and others, we have our normal employers, and we just go there, we volunteer, we sit on committees. It's a diverse group of people, so you have, people from industries, you have consultants, you'll have people who make equipment, you'll have people who, firemen and fire marshals, and insurance representatives. So it's a group of people that are familiar with industry from different angles come together and write these standards. So several of the standards were recently updated. So NFPA 652, which is the fundamentals of combustible dust, was updated. It's the 2019 edition, but with NFPA standards, they're kind of like cars. So the 2019 edition came out in 2018, and the 2020 editions are going to come out in 2019. So most of the other standards are coming out this year, even though they'll be the 2020 editions. So NFPA is charged with creating fire standards for fire prevention and fire protection. NFPA doesn't have any enforcement power of its own, so you don't have to worry about the NFPA police banging on your door, let me in. It's a volunteer organization. But since they don't have any enforcement power of their own, they rely on authorities having jurisdiction to basically enforce their standards. So authorities having jurisdiction, typically you think of those as like your local, fire marshal, or the people who issue building permits. So if you have to get a building permit, or if you need to have a building, business license, they might come in and say, okay, well, if you're going to have a building or business here, you have to design that structure, that building to be in compliance with NFPA standards. So that's typically who authorities have in jurisdiction are. But it can also be your insurance provider. So they say, hey, we're assuming the risk of your operation, so we're going to insure you only if you can, design your building in accordance with these fire protection standards. Because if you don't design them according to NFPA, then it's too risky for us to insure you. But then also OSHA. So OSHA relies on NFPA standards basically as a way to show like, hey, look, this is a recognized hazard. So, the woodworking, NFPA standards have been around literally since the 1920s. So that's almost 100 years of documents in place that say, hey, sawdust is a fire hazard. And if you don't deal with it, then you're ignoring a recognized hazard. And NFPA also tells you, how do you protect against those hazards? What can you do to keep your operation safe? And so if you ignore those hazards, you fail to recognize an existing hazard in place, and you fail to do anything about it. So you haven't followed the standards, you haven't put in the explosion protection or the sprinkler systems that NFPA standards require. And one thing with NFPA is that a lot of the compliance, so if you have a dust collector, NFPA says if it's handling combustible dust and then there's an explosion hazard, it needs explosion protection. That falls on the facility itself, not as much the equipment manufacturer. So if you're buying a piece of equipment, if you don't specify, hey, I want this dust collector to comply with NFPA, I want the airlock that's under the dust collector to comply with NFPA, the equipment manufacturer, they might not sell you that. They want you to buy their dust collector, their backhouse. And it's a lot cheaper to sell you one that's not compliant with NFPA. And they can do it if you don't ask them to. So it falls on the facility itself to make sure when you're adding a piece of equipment that you do the hazard analysis, you understand what's required by NFPA, and you make sure that the people selling you that equipment or maintaining that equipment, do it in accordance with NFPA. So what standards apply to combustible dust? That's a long list. It's a lot of standards, and a lot of times people, it can be very confusing where to go with the different standards. So you have NFPA 650 on the fundamentals of combustible dust. You have several commodity-specific standards. So NFPA 61 specific for agricultural and food processing. 654, it started out mainly being in like pharmaceuticals and chemicals and dyes, but it's been expanded over the past 15 years or so to basically cover everything that isn't specifically covered in 61 or 664. And 664 is for wood processing and woodworking. Then you have other standards. Yes.
On 664, if you have a facility or a carpenter shop inside or as part of your maintenance facility, does 664 apply to your interior carpenter shop?
So 664 has when it talks about applicability, it has basically a square footage that says once you get over this square footage, I can't remember exactly what that is, and that's when 664 comes in for woodworking shops and that. So, but the way you would want to approach that, so you can choose, and I'll explain that a little bit. Actually, I'll go ahead to the next slide and explain how you choose which standards you want to apply to the facility. So in general, NFPA 652 is an overarching standard. It applies to everybody that has dust, not just combustible dust. It actually talks about, if you have questionable material, if you're not sure if it's combustible, it talks about how you can do sampling to make sure it's not combustible. And then once you get that sample result saying it's not combustible dust, you can basically stop. You don't have to worry about the rest of the standard. But it covers everybody. And then NFPA 61, 654, and 664 are what's called commodity-specific standards. So really what you want to do is start with NFPA 652, and then that covers most of your process, like your management systems, your how you do testing, how you do hazard analysis. And then when you get into those specific pieces of equipment, like, okay, I have a grain silo. That's when you would go to NFPA 61. Okay, because NFPA 61 talks about a grain silo. Might talk about a raw grain bucket elevator. That's not going to be in 652. And it's currently written when there are differences. So if, say, 652 doesn't address something, or your commodity-specific standard doesn't address something, or maybe they talk about them in different ways, it's up to you as a user. You can decide which one you want to comply with. So NFPA has a long-term goal to combine all standards into 652, and that process started back in 2011, and it's finally really making headway. So we actually have a conference call next week to discuss how that's actually going to happen. So I think in the next few years, it won't be so confusing. You're not going to have that long list. It's going to be just NFPA 652, and it'll have sub-chapters. So everybody's going to have to do the same testing. Everybody's going to have to do the same dust hazard analysis. Really, the sub-chapters will come when you get into specific pieces of equipment. So you might have a sub-chapter that talks about, food processing equipment. A sub-chapter talks about wood processing equipment. But it'll all be in one place. So if you're trying to figure out what I comply with, you don't have to look at so many different standards. So what are the major requirements of NFPA? What does it make you do, or what does it say you should do? So first, it talks about, establishes how you lay out and design a facility where you're going to have combustible dust. It talks about separating dust hazards from other hazards. So how you don't. One of the things about the Gideon flour mill, that mill was the whole area where there was nothing left. In that picture, there was just basically a white, concrete pad. That was their warehouse area. So there was dust that was going from the processing into their warehouse, and that's why it just completely leveled that, because they weren't properly separating, where you're generating combustible dust from places where you normally wouldn't have combustible dust. So dust is going to waft through the air. It's going to deposit in places. So NFPA talks about how do you separate those areas in your building. All the standards require you to learn about the properties of the material. How easy is it to ignite the dust in your process? Is this dust non-combustible, and this dust is combustible? Like if you have a cement plant, you might have some starch, and you might have some rock, other material. Well, the rock dust probably isn't combustible, but the starch might be combustible. So you need to know which materials are combustible, which aren't. You need to have an idea of how dangerous are they. Magnesium dust is extremely powerful. It's easy to ignite. Flour dust, flour dust is combustible and it can do a lot of damage, but it's nowhere near as dangerous as magnesium. So you have an idea of what's the relative level of hazards with the material we're dealing with. So NFPA also requires you to conduct the dust hazard analysis prior to installing equipment, and for existing processes, it established a 5-year deadline, which we'll talk about in a little bit. The NFPAs also have prescriptive requirements. So this is, it's going to be something like if you have a dust collector with an explosion hazard, you're going to put explosion protection on it. Or if you have a conveying system, you need to, have adequate maintenance on the bearings so that the bearings don't wear down and create an ignition source. It has these prescriptive requirements for, ducting systems. And, so it goes through in there and talks about, hey, if you have this piece of equipment, this is how you should keep it safe. And then it also establishes specific management systems. So it talks about management of change. If you go in and start modifying a piece of equipment, or you bring in a change of material, you need to look at it, consider what are the safety implications of changing a material. So if back in 2012, there were several explosions in sawmills in Canada because there were beetle-killed trees. So the pine beetles came through and killed a lot of the forest in British Columbia. Well, these sawmills, they still had to operate. So they went out and they started harvesting these trees that had died out in the forest. Well, they had died and they'd also dried out. Well, they started processing these dried out trees on equipment that they had used to process green lumber, which had wet, still has sap in there. It's, if you ever see green sawdust, it doesn't really form a dust cloud. It sort of clumps together and falls down. And then it's got 50-60% moisture content in it. So when you try to burn it, you have to evaporate that water out before it burns. So you're not going to have a flash fire. It's not going to evaporate the moisture out of that green sawdust. But these sawmills, they didn't really have a combustible dust hazard because they were using green, processing green lumber. But when they started processing dry lumber that dried out in the forest, they brought it in. It was dry wood dust. On this equipment, it wasn't designed for that. There were several explosions just in a few-month period. And WorkSafe British Columbia, which is their equivalent of OSHA, put a moratorium on sawmill of dry, beetle-killed lumber until they could address the hazard, figure out how can they do this safely. So these management systems are talked about in NFPA, this management of change, the hazard evaluation. All this is talked about how you have to have that system in place. It talks about housekeeping protocols, employee training. All this stuff is addressed in NFPA. Yes.
Is that in 652?
Yes, those management systems are in 652. It talks about management of change, and those are slowly rolling out to the other standards. So there was an MOC requirement in NFPA 61, and the next version is going to be more stringent. They were kind of lax. The NFPA 61 committee, it's interesting. The different committees have different personalities, and some people take hazards a little more serious. Some people think, no, just keep going. But they're starting to really come together and coalesce on what the requirements are. So there have been some recent changes. So if you're someone who knew about NFPA standards that are pretty knowledgeable of it, there have been some recent changes. So with NFPA 652, it previously had a deadline to complete dust hazard analysis for your existing processes. It was 3 years after the date of the initial issuance of NFPA 652. That would have been September of last year. So they last year they issued an extension. All the other standards gave people 5 years, so they just went around that. So now the standard to complete dust hazard analysis of DHA for existing processes is September next year. They've also added the requirement that you can't just do an initial DHA and then walk away. You have to revalidate it every 5 years. It's basically like the PSM requirements require if you do a process hazard analysis, you've got to revalidate it, come back, review it, because there's going to be changes in the standards, there will be changes, little minor changes in your equipment, and just continual improvement. We're always learning, so you want to come back, and some of the assumptions you make in your dust hazard analysis might not be valid. You might say, oh, we'll never have a fire here. Well, 5 years later, you come back and like, actually, we had a fire every 6 months there, so maybe our assumptions are wrong. Those commodity-specific standards are being reorganized, so if you knew the standards before and you see the new standards, the chapters might be in different orders, but it's all with the goal to align with NFPA 652. They're more consistently talking about explosion protection and limiting explosion protection for vessels that are greater than 8 cubic feet. So NFPA's goal there, 8 cubic feet is about the size of a 55-gallon drum. So NFPA is making it sort of clear that they're not expecting people to go through and put explosion protections on some, tiny cyclones or just a little vessel that's smaller than the size of this drum. There have been significant updates in the housekeeping details in NFPA 652. Before, it just sort of said do good housekeeping. Now there's a whole chapter that talks about, hey, if you're going to sweep, sweep this way. If you're going to vacuum, vacuum this way. And it just gets into more detailed instructions on how to do housekeeping. And then there were some exemptions. There used to be, you didn't require a deflagration isolation for ducts that were less than 4 inches in diameter. That exemption's been removed because nobody could figure out why that exemption existed, other than somebody said, no, don't worry about 4 inches, but they're bringing that back.
Is there a basis behind that 8 cubic foot volume in particular?
I think it was just a risk-based. It was about the size of a 55-gallon drum. And as I mentioned before, when you have solid material, that expansion is like 1 to 8. So they figured if it's 8 cubic feet, then you have an explosion, and it impacts an area of about 64 cubic feet. I mean, yes, if you're right there next to it, that's a really bad day. But just, they really wanted people to focus on the highest hazards. So at the end of, when I go through what a DHA is, we talk about just risk. It's severity and likelihood, and those come together to identify risk. So I think that's it. They just didn't want people, to spend a lot of money going after low-risk items, and just figure that the money would provide more protection if you do better protection for bigger vessels and not spend so much money going after the little ones. Yes?
These details on the housekeeping, are these currently available or they're shortly forthcoming?
So, though, if you get the current version of NFPA 652,
Yeah.
so they're going to be in there. And if you get the standard, there's a little next to the code, it'll have a little N. So chapter 8.3.4, if it has an N next to it, that means it's new. So you can go to the housekeeping section, look for things that have a little N next to it, and you'll see how much new data is in there. All right, so now we're going to conclude. I'll talk about how to assess the hazards. So in your facility, how do you do a dust hazard analysis? How do you identify the hazards in your process? So basically, the potential for dust fire is going to vary from facility to facility and process. The process, even if you are handling the same material, just those details of your specific site, your specific equipment are going to be different than your neighbors. So in order to determine the specific, where do you have deflagration hazards, where do you have fire hazards, where do you have explosion hazards, you do a dust hazard analysis. So NFPA 652 has specific requirements, hopefully that's big enough to read, for DHAs. As I mentioned before, DHAs must be completed for existing processes by September 7th of 2020. But there are already news reports I've seen, evidence that, OSHA's, asking people to, don't wait on the deadline. We've already seen citations issued for, VPP sites. Don't have to worry about that too much, but non-VPP sites have been cited for not having a DHA. Even though the deadline hasn't come, OSHA still says, it's a good process and you need to identify the hazards. So for new processes or processes undergoing modification, a DHA should be done as part of the process. And if you're familiar with PSM, you want to do that early. Because if you come through and you've already issued POs for the equipment and you already got the manufacturer's already started in their shop putting together the silo or whatever, and then all of a sudden you do your DHA and say, boy, we need an explosion protection on that. Well, that's going to delay the project. You're going to have to stop the vendor. You're going to have to issue a change order. They might have to, retrofit something that, they could have easily, built something that has explosion protection on it. It's a lot easier than building something than retrofitting. So that's why you should do a DHA early in the process of a new project. They need to be led by a qualified person, so it needs to be someone who is familiar with the specific hazards of combustible dust, and also has some knowledge or some understanding of the materials that you deal with. So when you're looking for a qualified person, it can be internal or external, but they just need to know, about dust hazards, how to identify dust hazards, and then they also need to know about the materials that are specific to the project or the facility you're doing it for. And then DHAs must be reviewed and revalidated and updated every 5 years. Again, it's continual improvement. It's just you're continuing to learn things about your process. So when you look at it again, it's good to say, okay, we had this assumption and it's changed now. So what is a DHA? So it's a systematic review of the process to identify where fires and explosions can occur, identify the causes of those events and the consequences, and ultimately to determine if the existing or if it's a new project, the proposed safeguards are adequate to keep the risk at your facility at an acceptable level. So what are the steps? And I'll go through these in detail. So one, you want to evaluate the material being handled. Create a list of the processes that are handling those particulates. Then with that list of equipment, you identify where there's fire, deflagration, or explosion hazards. Then look for potential ignition sources. Discuss the fire and explosions scenarios. So talk about the consequences of these fires or explosions. Review the safeguards that are in place to mitigate the hazards. Evaluate the level of risk to determine if those safeguards are adequate. So first, evaluate material process. So you want to identify all the potential dust that are either handled, so if you get, say, powders as raw material, or that are generated. So if you have, some type of, grinding or sawing operations and you're generating dust, you want to, just identify all the dust, the different dust that are at your facility. First step is if it's a powder or something easy, you might be able to look at the safety data sheet. When we switch to the GHS standards, it's just, those standards specifically require that the manufacturer of the products or materials identify combustible dust hazards, so hopefully it's on safety data sheets. And a lot of times you'll just see, hey, this material can be a combustible dust that's suspended in air. And that's sort of like a blanket statement you'll often see. But if you see that, at least you know that, hey, if we're generating dust from this material, it's possibly combustible dust. As you know, not all vendors and material manufacturers are doing that with their safety data sheets. Sometimes they might have missed that. They might not identify it. Or if you have something that really, you're handling the product, or it's something that, food, not all food has to have safety data sheets, something like that. You can also look at textbooks and online databases. So NFPA 652 has an appendix that has a lot of material information on whether it's combustible dust. But ultimately, and especially if you're designing explosion protection, You need to know the specific properties of your dust, because those values in the textbook might be different, and you don't want to, those explosion properties are very important for explosion protection design. So if you are doing that, you want to conduct laboratory testing to get the specific properties of your material. Or sometimes if you just, you look into databases, you look in NFPA, you look on safety data sheets, you just don't know, then you might want to just at least do a screening analysis. Say, is this combustible dust or not? The next step, and one of the most important ways of making sure you just efficiently do a dust hazard analysis and make sure that you don't miss anything, is to come up with a really comprehensive list of equipment that handle combustible dust. And this picture is from NFPA 652 when they called through an example of how to do a DHA. And the types of equipment you want to, really pay special attention to when you're writing your list down. Pay attention to bins, tanks, and silos, those places that store particulate material. And when you're loading in, like I said before, you can have that dust cloud. Look at hammer mills, pulverizers, grinders, things like that. Particle size reduction equipment, those are all potential ignition sources. So your hazards going downstream of those pieces of equipment are going to be greater than hazards where you don't have that in line. Same things with dryers and ovens. Those are potential sources of embers in the process. Look at dust collectors. Look at the conveyors, things that are handling particles, and also sifters, screeners, classifiers. So basically, just come up with a list. Like they show here, just write down numbers for all the pieces of equipment that you want to include in the DHA. And then also write down the areas of the building. So you want to identify these are the rooms where you can have combustible dust buildup. And then for each of those items on your list, you want to look at one of the material properties. What type of product is this handling? How easy is it to burn? And determine is there a dust cloud inside this vessel or not? Is it an open belt conveyor, so I don't have to worry about there being a confinement in there? Or is it an enclosed conveyor? How far from a transition point? Where are these dust clouds going to be located inside the piece of equipment? And then for buildings, you want to identify areas where dust can accumulate. So you'll do this just by doing a walkthrough, looking where's dust located in this building. Periodically, get a lift in there and lift up and check the rack, check the overhead surfaces, make sure there's not dust where you weren't expecting it. And then also consider what upset conditions could create a dust cloud in a room. So I was doing a DHA at a bakery one time, and I went through there, and I would eat a piece of bread that fell on the floor there. It was just spotless. It was great. I was like, oh, your housekeeping is really amazing. Your dust collection is good. Is this how it always is? They're like, yeah, it's always like this, except for those 2 times a year we'll blow a pneumatic conveying line, and then we just blow the flour into the whole room. So it's not always just dust accumulation that makes a room dangerous. It can also be process equipment. Like if you have people that manually handle say sacks and are loading it into a mixer. What happens if they drop a sack? Dust. How far would the dust cloud go? So those are all the things you consider when you're looking at the building itself. Not only where is dust accumulating, but what could happen that could create a dust cloud. And then you look for credible ignition sources. So the things that you want to look for, process heat. So you have dryers in a process or any place where you're heating up the material, you can get self-ignition or create embers that go downstream. A common source of ignition or friction, so just bearings or moving parts inside pieces of equipment. Belt conveyors, you might, if the belt gets out of alignment and it starts rubbing on the side, you can generate frictional heat. A big issue is hot work. So I'm sure most people here have a pretty good hot work program. A lot of places I go to, when they think about hot work and they say, oh, remove combustible material, they say, okay, I'll move this this gas cylinder, or I'll move this cardboard box, I'll move the the gas canister away, I'll make sure there's no aerosol cans or whatever around where I'm doing hot work. But they forget to clean up the dust on the ground. They forget the dust on the wall. So if you have dust in the environment, make sure your hot work procedure includes washing down the area, because hot work can create explosions or be the ignition source. We were at a wood pellet mill and they had 2 open conveyors outside. They were doing one, it was a completely different process line, but the guy was doing hot work, and the flame from one hot work fell into the open conveyor for a different process. And it started creating an ember, and that went to a silo, and they had an explosion silo from hot work. On a different process, it was just close enough to where that ember went in there. You also have mechanical energy, as I talked about before. This particle size reduction equipment, milling equipment can create ignition. You also look for electrical sparks and arcing. So if you have a room where combustible dust is in there, make sure you determine if it's a hazardous location. So it's a class 2 location. If you have frequent dust clouds or potential to be in an ignitable atmosphere, it might be a class 2 location. Static electricity, especially when you're doing pneumatic conveying, removing of particulates can be a hazard. Radiant heat, hot surfaces in buildings can ignite dust. You also have open flames, so space heaters or just pilot lights, things like that. Powered industrial trucks, especially if they're diesel or some type of fuel fired. Even battery powered trucks can be an issue if they don't have certain protections in place to minimize sparks or whatnot. And then once you've looked at where do dust clouds or where do accumulated dust exist in my building, in our process, in our factory, where are there potential ignition sources, what can happen if there is a fire? Do we really only have a chance of a fire here, or can we have an explosion? So you just were taught through what will happen. And the things you want to consider, what engineering controls, what safeguards are in place to mitigate the hazard, and what additional controls might be needed. What types of equipment and occupancies are located near where that dust explosion or dust fire hazard is. What type of pieces what type of equipment are connected via ductwork? That way you can determine when will a hazard go from one place to another, and if there's an explosion in this piece of equipment, what all is impacted? And what's really the chain of events that can occur? As I mentioned earlier, it's like, that this firecrackers going off. So when you want to consider the consequences. And then once you've considered the consequences, you evaluate the risk. So in life, you can't get rid of all the hazards, but what you can do is reduce the risk. And really, risk is a combination of the severity of an event and the likelihood of an event. And what do we find is acceptable? So with likelihood, you want to consider, what's the potential? How likely is it for there to be a dust cloud in this area or this piece of equipment? Is it long conveyor where there's no material being added, there's not likely to be a dust cloud, or is it a bin where there's always during filling there's going to be one? What's the likelihood of an ignition source? And then you want to consider all operating modes, because most of the time explosions don't happen when everything's going perfect. So you want to consider, what happens when we're starting up the process? Is it different than when we're normally running it? What happens when we shut down? What are some of the expected failure scenarios that could create a process upset? And look at that too, as far as what's the likelihood of there being an event. And then with severity, not all dust explosion hazards are the same. A backhouse that's elevated 40 foot, up in the air on the back of the property where nobody ever goes. If that explodes, the severity of that is a lot less likely than a dust collector that's right next to the packaging line and on the employee walkway. So you determine the severity. That will be controlled by how close is it to employees, how close is it to other pieces of equipment, how large is the vessel. If this goes boom, is it going to impact a lot of people, or is it a lot of area? Severity can also be tied to how critical is a piece of equipment. So if you have a single bottleneck in your process, one conveyor that handles all of your product, if that conveyor goes down, then your plant's not operating. The employees don't have work to do when they come through there. If you have a piece of equipment that the lead time to replace it is 6 months, and it's a critical piece of equipment for operation of your plant, you're going to want to say the severity of a dust explosion, even if it's 40 foot high away from employees, it still might be a significant hazard if it shuts your plant down for 6 months and people, don't have anywhere to work. So you basically come up with, what's the level of risk, and this helps. This will help identify areas where the risk is unacceptable. So you might say, yeah, there's an explosion hazard here, but it's very minimal. And if we're going to spend money, we have a limited budget. I don't think anybody has an infinite budget to say, okay, I can spend $1 million to go after dust explosion hazards. You can't do that. Most people have to say, we've identified these hazards, we have a 3-year plan or a 5-year plan. And that risk matrix is going to help you say, hey, look, we need to do these in the first 3 months. We can do these the next 3 months. And you come up with, you hit the highest risk up front. And then, the lower risk, yeah, you want to address them, but, apply that to next year's budget. And that's really how you want to go through and use that risk analysis. So that's the end. Are there any questions that you have today?
Question. What I have found in VPP audits as well as in internal company audits and things of that nature is that there aren't a whole lot of experts who can come in and assess the dust hazards. And so they take a look at the NFPA requirements and they read into that, okay, you have to test every dust in your facility. Right. Even if it's dust on a table out in a warehouse, where you have forklifts coming in and out of a gravel yard. And I know that that's not a combustible dust, but we still have to do the testing. And, every one of those samples is $10,000. How do we address that? I mean, NFPA obviously wants us to put the money where the risk is.
Right.
But the way we're doing VPP audits, for instance, it seems like it's driving us toward the opposite.
And spending more money on laboratory analysis than on taking equipment. So NFPA does address that to an extent. They say if you have knowledge of, you can apply knowledge of the material or to go towards that. And a lot of times, it's important to do testing of the material, but you don't always have to do it. I don't like to start with material testing. I like to look at the process first, say, what do we know about this material? I mean, it might, if it's flour, I know it's combustible. If it's dry sawdust, I know it's combustible. I don't have to do.
Polyethylene is combustible.
Mm-hmm. Yeah. So polyethylene is combustible. So I start that way. What do we know about it? And I really only recommend testing to identify the gaps. So if you want to, design exposure protection for this specific dust collector, and it's a mix of materials, then I would say, yes, we need to test that material because we can't just look at, it might affect the way we design that piece of equipment. So, that's the way we tend to approach it. But you're right, there's not a lot of...
Yeah. When the auditor says, okay, you have to do this in order to get your VPP recertification. I would recommend, you maybe have a form, just like in environmental people, you have a waste determination form, so you can do something similar with dust.
Did you do your dust hazard analysis just in the DHA?
Yeah,
Does it apply to the dust?
That's typically how when we write a dust hazard analysis, we have a whole chapter on materials process, and we'll have a narrative discussion of, hey, this is kaolin or this is gravel dust, and so it's not combustible. And we put it, we'll have a table there, and we'll say identify it as non-combustible, explain why we identified it as non-combustible. So, I think it's documentation. If the auditor does, auditors are going to audit. That's one thing I've always learned. Auditors don't like to go to a place and say, hey, everything's great. They feel like they haven't done their job if they don't come up with something. But just document it, maybe quote that section of NFPA 652 where it says very clearly you can apply knowledge of the material can satisfy Chapter 5 of NFPA 62.2 where it talks about the material evaluation. So if you just document that, show it in a table that, hey, we've looked at it and this is why we determined it's not combustible. You know, I can't guarantee you a specific audit. You know, I don't like saying it's going to pass an audit because auditors are people. There's too many people that tell you how they're going to treat something.
Yeah, well, the other issue is they always want testing at that specific facility on their dust. So we may have, 20 different facilities that all have the same dust. We've got to do testing at 20 different facilities.
Yeah, they're, I typically wouldn't recommend doing that. But we also, we have a partnership with Fight for our testing, so we don't have our own lab. A lot of the other consultants have their own testing lab, so they might, they'll get more of a fee from testing two materials than they will from doing the actual DHA. So there are some advantages of that there.
In Florida, it calls out cleaning of wet collectors. It seems to specify that you need to clean the wet collection unit daily. If you have a process where you don't have that much water, is there a way to justify not cleaning?
Yeah, one of the parts of the DHA, when you look at it, you want to, identify material, production rates and the time it's in there. Most of the standards in NFPA, when you talk about prescriptive requirements like that, there's sort of a caveat, an unwritten caveat. Sometimes it's specifically written because, it's so common. But there's an unwritten caveat in the NFPA standards that you can do a risk analysis to determine which of the prescriptive requirements, you have to follow. So most of the time, if there's a requirement for your specific process, that it doesn't make sense to do it the way NFPA says to do it. And they also have an equivalency. So there's in the clause, like in the very front of NFPA, Chapter 1 almost, there's an equivalency clause that says that if you do something that's just as safe as what we say here, as long as you document and justify why it's just as safe, you can do that. So that would just be another case. You do risk analysis, you document why less frequent cleaning would be more safe. Maybe there's some hazards that are created during the cleaning process. So if you clean at less frequency, the employee who does the cleaning might be exposed to less hazards. So you just document that the risk of not cleaning it more frequently is low, and it doesn't justify it. As long as you document that, explain why it is, maybe throw a clause in there where it talks about, having a risk analysis acceptable to AHJ or equivalency clause if you want to pass that audit. Just document why you made that assumption and what the assumption is based on. Any other questions? All right, if anybody wants a copy of the presentation, just let me know. I have the cards up here. I'll be happy to email them to you. But thanks for your attention.